Okay, welcome back. So when we finished our analysis, we wanted to know how would the exit temperature for my cooler here, how would that temperature scale with fan wind speed? Well, we have all the governing equations on the screen here, so we just need to make sure that this wind speed actually gets into this expression that we use to solve for the exit temperature. So again, we take that form of the expression we had before, where we had the mass flow rate, and all we need to do is substitute in this expression, which includes explicitly the velocity of the air. So we can see the density effect, the area effect, the wind speed, and of course the specific heat. So the temperature scales within this bundle of variables as a function of velocity. So it's a little bit complex. It matters what this number is here as to whether or not we could say, like if we had a very low entrance temperature, we could say, well, it scales inversely proportional. But for the system that we were considering, remember, these numbers were, the entrance temperature was significant, and this temperature increase was about 20%, a little bit less than that in terms of the relative to the entrance temperature. So we can't quite say it's inversely proportional. There's some weighting associated with that entrance temperature. But it shows you how, again, you might set up a spreadsheet and look at the range of velocities that you could achieve with a typical box fan. Cool. All right, so we've now done a number of different examples for kind of turbo machinery, for compressing air, compressing fluids, flowing things, heating things, cooling things. Now I want you to consider one of the hardest systems to analyze, and that's a time-varying or a transient system. So for this example, it's going to seem really simple on the outset when we just consider the system in general. But when we go to actually analyze a system, we'll see how hard these time-varying systems can become to actually get answers for, get numbers for. So the system we're considering is a car tire that's low on air. So we're going to assume we have a really good air compressor that we're going to use to fill this tire. We're going to assume it has a really large reservoir tank and that air is at ambient conditions, 20 degrees C, and that the reservoir is filled to about 350 psi gauge. Our tire, which is about 10 liters in volume, so this is a typical passenger vehicle tire, initially has air at 15 psi and 20 degrees, so ambient conditions again. Now, that's a pretty low number. This is my aside on being a good citizen. You always want to inflate your tires to the appropriate level because it really does have a significant effect on your fuel economy. So we would hopefully never let the air pressure in our tires get that low, and this is kind of an exaggeration just for this example. So again, be good citizens. Keep your air pressure at the appropriate level in your tires because it does have a very significant and direct effect on your fuel economy. Okay, so there's our public service announcement. So our tire is low. It has 15 psi. We want to fill it till we reach the recommended value of 35 psi. So passenger vehicle tires are about 30, 35 psi. If we assume the tire fills very rapidly, so we're going to take our hose from our compressor, we're going to fill the tire. Let's assume the fill process is very fast, so we can assume that process is adiabatic. How much air in mass do we need to fill the tire from 15 psi to 35 psi? And can we determine the temperature of the air in the tire after we finished filling the tire? So these are linked questions. I'll tell you right now they're linked. We would essentially need to answer both questions simultaneously. So again, we need to define our system. Okay, so we have our tire, which has a known volume. We know that some initial state 1, we have pressure of 15 psi within the tire, and we have an initial temperature of 20 degrees Celsius. We're going to define our system as the air within the tire. I don't want to include the mass of the tire, so I'm going to put my system as being the volume of air within the tire. We're going to assume that tire is a nice beefy steel-belted radial because I want to assume the volume is constant. that there isn't any significant volume change. That's going to simplify our analysis a lot. And hopefully the minute I said we're going to assume a constant volume and no volume change, you're thinking, now I don't need to consider any expansion or compression work that occurs during the process. So this is a very big assumption. Not a big assumption, it's an important assumption. I'd argue it's a pretty fair assumption in terms of the volume isn't going to change much. So we're not going to lose too much of our energy to expanding the volume of the tire. Okay, so we have our initial state. We've defined the volume of our system. At the final state, we know we're trying to hit a target of 35 psi. We're told that the fill process itself is very fast, and again, we can assume that that process is adiabatic as a consequence of it being fast. And ultimately, we're trying to find the temperature at the final state. Okay, so we've defined the system. Check. Now we need to identify the proper forms of the conservation of mass and conservation of energy. So we look at remember, always use the most general form and then invoke your simplifications. So we say that for the conservation of energy, we have the change in the mass and the control volume is balanced by all the mass flow rate into the system and all the mass flow rate out of the system. Well, there's nothing coming out. We hope there are no leaks in our tire. So we're going to assume no leaks and there's no mass leaving the system. And so what we're left with for the conservation of mass is an expression that looks like this. There's one mass flow rate into the system. That's me filling my air into the tire, right? And we know that there has to be a change in the mass within the control volume. That's what we're trying to achieve. We're trying to put more air into the tire. Okay, so now what I have is a differential equation. Whereas before, when we were considering the continuity expression or the conservation of mass expressions, they were nice and simple constants. Now we have something that looks a little bit harder to work with. So we're going to take that mass expression there, and we're going to see, that's simplification. And in order for us to determine the total mass that enters the system, we're going to have to integrate this expression as a function of time. So we're going to have to integrate from the initial state to the final state, from state 1 to state 2. Okay, whenever you see an integral expression, you always have to look at these variables, just like we did with expansion and compression work, where we had to understand how the pressure would vary as a function of volume. In this case, we have to understand how the mass flow rate varies as a function of time. Now, all the language I used in that problem statement, that language was trying to get you to focus on, okay, if I have a large reservoir tank and it's at a pretty high pressure, much higher than the pressure in my tire, in fact, it's an order of magnitude higher, what does that mean? What we can assume, I'll tell you what that means. That means that we can assume that the mass flow rate is constant as we fill the tire. And this is something we're going to need, this is information we're going to need next, that the state of the air that is in the tank doesn't change as we fill the tire. So in other words, we can't bleed the tank dry. We can't decrease the amount of material in the tank so much that we affect the state conditions within the tank. That's our assumption. And as long as I have a really high quality compressor with a large reservoir tank at a very high volume and pressure, that assumption is a good assumption. So we assume the mass flow rate is a constant during filling. If you had a little compressor with a little volume, that's not going to be a good assumption. And we'd have to actually consider how would the mass flow rate vary as a function of time and solve that integral expression. Okay, so let's keep going with this. So now we've set up the conservation of mass. Now we need to consider, okay, we've got this integral expression for the conservation of mass, which says this. from state 1 to state 2. And we've just said we're going to assume this mass flow rate in is a constant, so that lets us say, okay, m dot delta t, which essentially is the mass into the system. And then on the left-hand side of this expression, this is pretty simple. This is just the mass at state 2 minus the mass at state 1 is exactly identically equal to the mass that's been added to the system. And that's very intuitive, and many of you may have just written that down for the conservation of mass. You may have just said, hey, look, the final mass minus the initial mass is how much you added to the system. Of course, except if you did that without going through the thought process of considering the mass flow rate during fill, you skipped a really important step, and you skipped something that's very important in terms of understanding what assumptions were implied with just writing this down exactly. So again, be very careful and walk through the system and make sure you understand what assumptions you've invoked. Okay, so that's our conservation of mass. The conservation of energy has to have exactly parallel structure. Okay, so let's look at that. And again, we'll set it up in its most general form, and then we'll simplify it. Okay, so here's the conservation of energy, most general form. Well, we've already said we're going to consider the process fast and therefore adiabatic. We've already said the volume is going to be fixed. We don't have shafts, electrical cords, anything entering in the system, so we're not going to have any work in the system. So no expansion, and the most important one was the no expansion or compression work. We're going to neglect kinetic and potential energy effects. And of course, we only have mass entering the system. We don't have any mass leaving the system. And on the left-hand side here, again, we're still going to neglect kinetic and potential energy effects. And all of this leads to something that looks pretty elegant and simple. The change in the internal energy in the control volume has to be balanced by the energy introduced by the air entering the system. So it's pretty simple. Except again, I have a differential, so let's go ahead and put that in an integral form. So we have okay. So what we say is that, well, if I assume the mass flow rate was constant in my analysis of the conservation of mass, it has to be constant here too. And again, because I am assuming I have a large compressor and the state doesn't change, the state conditions, thermodynamic state conditions don't change in that air compressor system, I'm going to assume the enthalpy is also constant as a function of time. So I can pull both of these variables outside the integral, and it's just a simple expression. So again, we have the final internal energy minus the initial internal energy is simply the product of the mass into the system times the enthalpy of the air coming into the system. And of course, we have this expression here for the mass that is added to the system. So we can say U2 minus U1 is equal to M2 minus M1 times H in. And you're looking at this going, well, so far, I don't see anything that has an expression for temperature in it. Okay, so how am I going to find the temperature in the of the air in the tire from this expression? Well, hopefully you're thinking, okay, it's air. Let's go ahead and invoke some ideal gas assumptions, and let's see where that takes us next. Okay, so we're going to go ahead and invoke the ideal gas assumption for air. And what we see here is that we're going to go, let me just write this down and we'll discuss it. getting a little crowded here, and I apologize for that, but I want to keep all this on the same page so we can see everything together. So what we have here on the left-hand side is this expression for the internal energy. And it's the product of the mass at the final state and the internal energy of the final state, mass at the initial state, times the internal energy at the initial state. That's a 1. Okay. On the right-hand side, we have the difference between the mass at the final and initial states times the enthalpy at the entrance. Well, we know that the ideal gas assumption tells us the difference in internal energy, specific internal energy, is given by the product of the specific heat at constant volume times the difference in temperature. So we know this. Except we come down here and we say, hey, wait a minute, but the mass at state 2 is very different than the mass at state 1. So I can't factor the mass out of this expression. Okay. And on the right-hand side, I have enthalpy, which is a product of the specific heat at constant pressure times temperature. So I'm looking at this expression, and I can't find a closed form for me to determine temperature in this expression yet. Let's go through and again kind of think about this some more. We know the ideal gas assumption can give us some information about mass. So, for example, we know that the mass at the initial state can be given by this expression here. Okay, so we have the pressure at the initial state, we know the volume of the tire, that the specific gas constant, we've gone through that, and there's the initial temperature. Okay, fine. M1 can be considered fully defined. So we can go back and we can say, yep, I know M1. I can't find M2 using the same type of expression because, of course, M2 is a function of the temperature we're trying to find, T2. Okay, so that's unknown, and that's unknown. Okay. Enthalpy for an ideal gas is a function of temperature only. We know the temperature of the reservoir of the tank, so I could look this up. This I know. Okay. But I don't know M2, like we said up here, and I don't know U2, because again, the internal energy is a function of the temperature. So what I have here is an underdefined or underconstrained system. I can't solve for the temperature at T2 unless I have the mass at the final state. I can't get the mass at the final state unless I know how much mass I've added to the system. If I had those two pieces of information, I could find the temperature at the final state. Or if I could find the temperature through the conservation of energy equation, I could go back and find all these masses. So it's underconstrained. And that's because of the assumptions that we invoked on how the fill process occurs. So what I want you to think about is that, so I've already shown you, this is a really complicated problem. And we need to change the assumptions to make it tractable. So I want you to think about how might we change our assumptions about this fill process to allow us, we need another equation. So we have 3 unknowns right now, but we don't have enough equations. We actually have 4 unknowns, and we have 3 equations. So I need something else in order to make this, to actually complete the analysis. So what I want you to do is think about that. How might we change our interpretation of how the tire fill process occurs in order to allow us to answer this question? And we'll address that next time when you come back.